Okay, so let's begin today's CS seminar. Welcome, everyone. This is today's seminar is one of the seminars in the Gerald and Mason Distinguished Lecture Series. These seminars are here in celebration of Jerry Mason's distinguished contributions to the computing community within Johns Hopkins. So today we are very honored to have Aniruddha Kembhavi. He's joining us from Allen Institute for AI in Seattle, where he is a senior director of computer vision. Ani is also an affiliate associate professor in the Department of Computer Science and Engineering at the University of Washington. Ani is interested in problems at the intersection of language, vision, and embodiment. Ani actually obtained his PhD from our cousin university, University of Maryland, not too far from here, under the supervision of Larry Davis, where he spent wonderful years working on many exciting computer vision contributions. Among many awards that Ani has won are Best Paper Awards at CVPR 2023 and an Outstanding Paper Award at NeurIPS 2022. And today we are very glad to have him where he's going to talk about building foundation models for vision and robotics, a topic that is quite hot and timely for all of us. With that, let's welcome Ani.
Thank you very much for that kind introduction. As Daniel said, I went to graduate school not far from here, and I had many friends who went to Hopkins. So I frequented Baltimore very, very often to discuss work and to discuss how are we going to get out of this place? How are we going to graduate? So the deep questions that every graduate student has. Okay, so today I'm going to talk about the challenges in building foundation models for vision and robotics. Large language models are omnipresent, right? Everyone knows about them. Everyone is using them. They're powering search engines. They're powering ways by which we're finding information in scientific content, and they're even helping us code. And these language models are really beautiful because they are what I like to call truly general purpose, right? A single model, a single set of parameters is powering so many different experiences for users. And when I think about a model as being general purpose, I really think of it having three qualities. One, it has a general architecture that supports many, many different tasks. Second, these models can learn concepts from one data set or one skill, and then transfer that concept to a new skill. And then third, these models can learn new tasks very easily. And language models demonstrate all of these principles to a high degree. The story in computer vision has been a bit different. We're still trying to create the equivalent in computer vision in terms of a general purpose model. And one of the big challenges that we face in computer vision has been that our tasks are so heterogeneous. And as a result, unification has been very, very hard. So given an image, there's so many different pieces of information that you might want to extract. Sometimes you want to extract a piece of text, sometimes a bounding box, sometimes a more continuous signal like a depth map. And sometimes you want to go back into pixel space from structured inputs. And of course, I'm just talking about images here, but we have video, we have audio, we have 3D, and so on. The same goes with robotics, with an additional challenge is that unification is also hard in terms of physical embodiments. A lot of robot demos that you've been seeing recently in the news are on humanoid robots, but a lot of industrial robots simply have wheels, some have arms, some don't have arms, and so on. Robotics has another big challenge. In the language community, we have so much data online that is extremely aligned with downstream tasks. In the vision community, we have a lot of data online that is, in a way, loosely aligned with downstream tasks. In robotics, we have no data. Training data is extremely scarce, and real-world data collection is expensive. So here is a paper that came out a year ago or so, about 18 months ago, called the Robotics Transformer. And it introduced one of the largest robotics datasets to the community. It's a paper from Google. When I mean largest in robotics, I'm talking about 100,000 data points. That's very, very tiny compared to 3 trillion tokens that language models are trained on. And this dataset took 17 months to collect for a big company, right? So you can see that we're talking about very, very different volumes of data in language, vision, and robotics. So in light of these challenges, how can we start thinking about foundation models for vision and robotics? So in this talk, I'm going to talk about three different ways of thinking about this problem and addressing these challenges. First, I'm going to talk about a method to start unifying tasks so we can start thinking about general purpose models. Then I'm going to talk about how do we address the data scarcity issue in robotics. And finally, I'm going to end with suggesting an alternative paradigm to building these large foundation models. Let me start with the first one called unified I/O. Until not too long ago, the vision community was focused on building specialized models. And this is also after the deep learning era. And so specialized models meant that you chose a task, and then you found some data that was aligned to the task to help you do supervised learning. And then this model would perform that task and that task only. If you had to perform a second task, you built a second network from scratch. The next evolution of this idea, of course, was in trying to unify some parameters in the network. So have a set of core network parameters and then have task or even dataset specific heads. And so this was, of course, revolutionized by the advent of ImageNet, but the same idea has transferred into web scale image text data. So you pre-train some parameters, and then when you want to perform a task, you introduce some parameters on top of this pre-training backbone that help you adapt the model to that task. The problem is that every time you want to perform a new task, you need a new set of parameters. The next evolution was to say, well, we need to have more parameter sharing. We need to take a step towards general purpose models. And the obvious thing to do was to say, well, I'm going to start clustering tasks based on the kinds of modalities that they have at input and at output. And as long as tasks share the same modality, I would force them to share the same parameters. So this is a sort of architecture that said there's some cross-modal parameters that are shared, and then there's some image-specific encoders, image-specific decoders, and so on. As you can see, models have been evolving towards general purpose. And so what's the next step? How do we get true task agnostic models? How do we get true parameter sharing for all of these heterogeneous tasks? And this is unified I/O. So unified I/O at a mile-high level really looks like a large language model. It inputs a sequence of tokens, and it outputs a sequence of tokens. But unlike a language model, it supports more than just language. And so at the input, you can provide language, you can provide images, you can provide bounding boxes, you can provide all kinds of image-based inputs. And you can do the same at the output. You can use a decoder to decode language, but you can also use it to decode images, depth masks, surface normals, bounding boxes, and so on. As a result, a single model, importantly, a single set of parameters, can be jointly trained on many different tasks in computer vision and natural language. So how does this work? At the core lies a transformer architecture. We're all using transformers, and this isn't any different at its core. And this transformer accepts a sequential input and produces a sequential output. So tasks that have language involved are very naturally applicable to this sort of architecture. The interesting thing happens when you have a task like segment the cat. So this task involves generating a binary mask where every pixel on the cat within this image is labeled as 1, and every pixel that is not cat is labeled as 0. So you can think of it like a white mask on a black background. How do you start generating this kind of mask with this transformer decoder? So the key insight here is that we're going to use a very rich body of literature in computer vision called vector quantized models. And these models, in this particular paper, we used a vector quantized variational autoencoder What these models do is they take an image input and they use something like a convolutional neural network in order to produce a representation. But then this representation is quantized. And so the bottleneck representation that you have in an autoencoder, because it's vector quantized, it's a discrete set of tokens. The decoder is then able to accept the discrete set of tokens and reproduce the image. And so what we've got Unified I/O to do is, instead of predicting pixels at its output, what you should do is you should instead produce the discrete set of representations that a VQVA decoder can then decode this into the desired output. This suddenly changes the way of thinking about multimodal systems. Now, anything that can be serialized and deserialized effectively into a discrete representation can now be fair game for a model like Unified I/O. And that's why we've been able to not just do things like segmentation, but you can start doing depth estimation, you can do coordinates, you can do all kinds of representations that computer vision tasks typically use. Now that you have a unified model, you can start pre-training all of your parameters using web scale data. And that's exactly what we did. We took millions of image text pairs, and then you can do tasks like image denoising, text denoising, image text denoising, etc. And then you can multitask this model on many, many different heterogeneous tasks. What do you get as a result? As a result, here are some qualitative examples. So this is the first model. This was about a year and a half ago. This was the first model that could perform all of these different tasks using a single set of parameters. You can generate images, either from a text description or from simply masking out some portion and saying, hold fill these images. You can input a segmentation and output an image, or you can input a natural image and ask it to do tasks like surface normal estimation. You can also do structured prediction tasks, like produce bounding boxes or key points. This isn't very visible here, but these are key points denoting different joints on the human being. And of course, you can start decoding language. So now that we have established a method to bring in the image and text modalities, does this scale? And the answer is yes. So in Unified I/O 2, we decided to take this to the next level. We decided to say, well, image is just one modality. How about sequences of images? Sequences of images lets you do more interesting reasoning tasks across collection of images. Of course, sequences of images naturally tends you towards video. Now you can do the same thing with audio, and you can also start getting robotics tasks involved, right? And the idea at its core is still the same. Use a transformer architecture, use a vector quantized model in order to bring all of these domains into a discrete space, expand your vocabulary for your encoder and decoder, and then train this model jointly. Pre-training now becomes quite interesting, and some of the pre-training tasks can teach the model interesting concepts like 3D bounding boxes. So for example, in pre-training, we have not just text, but we also have image and audio. So now we have image text pairs that you can mine from the internet, but you can also mine video data from YouTube and start looking at image data. So looking at consecutive frames. You can look at closed captions produced by YouTube. So that's where you get interesting conversation data. Then you can also produce audio. Sorry, you can use audio. So now you have image frames, audio, and closed captions. And then, of course, you can also run computer vision models on this data in order to produce sort of synthetic data. You can say, I have audio, but I also have segmentation. And so you have many different combinations that you can use for pre-training. So in the text world, there's different kinds of pre-training that people do. And we've adapted these for the multimodal world. So for example, some of the kinds of pre-training that people do in text are denoising. So you can have regular denoising where you mask out certain patches, and then you get the model to predict what word or what byte token was present in that patch. You can do sequential denoising where you give the model a certain part of your language input, and then you have it auto-regressively generate the rest of the input. Or you can have extreme denoising, where you give very, very little of the input, and you get the model to predict large portions of your data. Now the same thing can be done across modalities because we're dealing with multimodal models. So here are some of the interesting pre-training tasks that we have. So this is, you can think of it as a stereo pair of images, which means you have one world, and then you have two cameras imaging this world. And so now you can mask out one of your stereo pair of images and give it information in the other image and have it predict the pixels in the first image. Doing this makes the model slightly 3D aware because it understands that this cushion here or this couch here must be present in this image because I'm looking at essentially the same object from a different orientation, from a different camera, from a different set of camera parameters. So this is an interesting pre-training strategy. Then, of course, you have, like I said, pre-training strategies by masking out one modality. So you can give it some frames, a portion of the audio, then give it the next frame, and then have it construct the missing piece of audio. So this can teach you about objects, it can teach you about affordances, it can teach you about how objects are used, what sounds they make, etc. Here's another interesting way to pre-train is to provide it with a frame and then provide it with some actions that a robot might take in that environment and ask it to predict its observations based on the actions that the robot could have taken. And so this is sort of what we call in robotics forward prediction. And so you have lots of interesting ways of pre-training your models in order to teach them different skills. Instruction fine-tuning is also very interesting when it comes to multimodal datasets. So a lot of multimodal instruction datasets are present in the image editing space. So for example, here you have, I'd like to take this cartoon and morph it in this way, or I'd like to take this frame and change it in this way, or I'd like to take a human pose and generate pixels from there. But what we're interested in is teaching the model tasks that are unseen in training data. And in order to do this, the way we did it is we started taking data sets that already exist in computer vision and trying to combine them to sort of have an exponential number of tasks that we can provide the model at training time. And so here's an example. So object detection is a task where you have an image and you simply have to draw bounding boxes around all of the objects and assign them categories. But now we can take an image like this and generate a synthetic task from it, for example, saying, detect all the carnivores in the image. So this requires the model to not just locate all the animals, identify the animals, then look at a knowledge base in order to see which of these animals are herbivores and carnivores, and then draw the correct bounding box. Or you can say, detect all objects that occur in multiple instances. So you can see here that you can take existing data sets in computer vision and modify them in order to creatively create a large volume of instruction data. I won't go through this crazy diagram that we have here, but it took us almost a year of work, 18 months of work in order to produce one of the largest instruction tuning data sets that are available in the academic community. And so we have about 120 data sets and 220 tasks that we use to train this model. So I'm going to show you some examples of what Unified I/O 2.0 can do. So of course, given an image, you can start describing the image. This is something very basic that all models can do. And you can ask it to describe it briefly. You can ask it to describe it in a detailed way. Then you can start messing with the image pixels. So you can ask it to remove certain objects. You can do style variations. You can ask it to render a sunset and so on. But now, because your model is multimodal in terms of language, vision, audio, and embodiment, you can do even more interesting tasks. So you can ask it to generate music for this scene. This is where I'm going to stop talking and unmute. So you can generate music for this scene. Then you can say, make this image haunted, and then produce music for that scene. So you can see that the model is able to associate words and associate what it sees in the image with some correlated audio, right? Then you can start doing tasks that are not present in the training data. So for example, we have a task of segmentation. We have a task of surface normals, but you can start saying, well, why don't you build a segmentation map, but only find me surfaces for which the surface normal is oriented upwards. And you can see that the model can start composing skills into new tasks. Here's an interesting one where we provided an initial frame, and we asked the model to say, choose an action that a robot can take safely in this environment. And then once you choose that action, why don't you generate an image that the robot would observe after taking that action? And then we sort of rolled this out. So you can think of this as the first steps towards building a world model. And what we see here is a hallucinated environment that the model has created starting from this location. Then we can start doing audio localization. I'll mute. So you provide that audio and you provide this image, and then it draws bounding boxes around objects that might have made that sound. And then you can do the same thing with robotics, where you can give it an image, you can give it some instruction, and you can ask it to produce actions by this robot that would allow this instruction to be fulfilled. And then you can put those instructions into a simulator and see if it was successful. So these were just results to give you a demonstration of what a unified model might be able to do in computer vision. And as you start getting more and more modalities involved, I think you can start building very, very powerful systems. So this is the first step towards true unification in computer vision. So next I'm going to talk about another problem in robotics, which is how do we generate pre-training data? Yes.
I have one low-level question about unified I/O.
Yes.
In the output of this architecture, do you always know what's output token corresponds to what modality? Are they like pre-specified boundaries?
So we have a different vocabulary. So you can think of your vocabulary as being partitioned into language tokens, image tokens, and audio tokens. And when you produce a word from which corresponds to the vocabulary on the image side, then you know that it's an image pixel, right? But of course, the way the data sets have been arranged and the way pre-training works is you don't just produce a pixel, you always produce a full image. And so you have a start image token, an end image token, and then you produce the number of tokens that are required to be put into the VQVA to produce the image. And so you always know by virtue of the vocabulary which modality you're.
Got it. Thank you. I have one more question.
Yes.
When you presented the success of unified I/O, which was wonderful, it seemed like the success is due to scaling the data set, the task diversity, and so on. Was it really the key factor here, or the scaling the model size or pre-training also played a key factor?
So I would say that we're still in the small scale domain. Although we have built a 7B model, language models really start getting very powerful at 70B scales. And when you start looking at multimodal data, I think you probably have to go beyond 70B. So I would say we're still operating in the small domain space because of the resources that we have. I think the key to getting this model to work was pre-training. One thing that I did not mention was that the goal of unified I/O was not to build a multimodal model. If that was the only goal, we would have taken a clip model off the shelf. We would have taken, Llama 2.0 and put them together in the sort of Lava architecture. We use no models off the shelf. Everything is trained from scratch. And so this was a demonstration of what multimodal pre-training can get. So I think that has been the focus of the project. Yes.
How do you switch between the decoders for tasks? For image segmentation, you have a decoder. Let's say for text generation, you have a separate decoder.
No, it's just one decoder.
It's just one decoder.
It's just one decoder with different vocabularies, right? I mean, that's not the right way to put it. It's one decoder with a large vocabulary, which is a superset of image tokens, text tokens, and audio tokens.
Oh.
Yes.
So is the dimensions of the embedding space much higher than what we see in like text embeddings?
Ideally, yes, we have not been able to increase the dimensions of the encodings a lot because of computational resources. Because, we have, as you increase the dimensions of your embeddings, the number of parameters in your model are going to expand a lot, which would limit the batch size that we use for training. And so because of certain constraints on capacity, we have kept our, I think our dimensions are 8192. I forget the exact numbers.
So, so if you haven't increased the dimensions of the embeddings, how is the, so would there be overlap in the, like when you, since it's a unified decoder, so you have like shared representations, right?
Yeah. So exactly. So what you're talking about is capacity issues, right? So if you have I don't know, let's say you have a 1024 dimension embedding which only learns language versus a 1024 embedding that learns multimodal, how is this going to perform? Well, it's not completely clear that expanding the dimensions can lead to better transfer across modalities. Bottlenecking has been shown to aid in transfer and aid in generalization. And so we made the choice to limit the dimension of the embedding space and not simply go with like what's used in language multiplied by 3. I also feel like as you have a lot more capacity in the dimension, you may lose some of this cross-modal behavior. That is a hypothesis. I haven't tested this. Yes.
So I guess like is that like one decoder, but it's not like the superset of the category.
Yeah.
So definitely you have that like constrained by the physical category of the decoder, or like that really analyze the new path which has never been seen.
Yeah, so some of the experiments that we have show the beginnings of generalizations to new tasks. I'm not going to claim that we're able to perform new tasks zero shot at a very high accuracy. But as long as the tasks are supported by the modalities that we support, which means as long as the tasks require you to produce either text or pixels or audio, it is at least able to support those new tasks. And for some tasks that are closely aligned with the skills that we have at pre-training, it shows a really good ability to perform those tasks. If you have a completely new task that has completely new modality, this is not.
Yeah, I have another question, which is like, to me, I feel like all the data right here is also like supervised data.
Yes.
Like, we all like supervised data.
Yep.
Is that a part of the problem where like the current model cannot scale up?
Sorry.
Is that a kind of problem where like the current model cannot scale up in terms of the data? We have like a huge limitation how to get the data. Is there any? I guess that's also the problem where like really hard to train the CL supervision data if you don't have this next word prediction. We find out that what's not.
Well, well, that depends on who you talk to, but I'm in the camp that supervised data is actually probably the best data source that you can use to pre-train these models. So in robotics, we use a lot of reinforcement learning techniques, and those scale up very, very well. So I would say that having supervised data is a good thing to do. In the vision space, there's a lot of work on masked autoencoders, and so you can start masking pixels and then using this as your equivalent of your next token prediction tasks. It is a problem. I do agree with you. And the reason next token prediction is difficult in vision is that next tokens are almost always highly correlated. So for example, if you have a video and you simply ask it to produce the next frame, there's a lot of correlation with the previous frame, which means that there isn't a lot of interesting gradient that flows back into the boundaries. In text, I am blank. There's a lot of variation, and there's a lot of interesting knowledge that you can add into the system by giving it supervised I am walking, I am talking, I am speaking, etc. Whereas in vision, a red pixel is almost always bordered by another red pixel. And in the next frame, that red pixel probably is also going to remain red pixel. Very, very few frames, very, very few pixels have any variation. And so that's why next token prediction is challenging. I hope that sort of answers your question. Okay, so as I said, in robotics, gathering large volumes of data is extremely challenging. I think the way to overcome this challenge is simulation. And at AI2, we've been building out a simulator to train robots in for several years now. And what these simulators allow you to do is the simulators allow you to have different embodiments, perform tasks, and get supervision in order to train your datasets. And of course, this is not a very unique position that we're taking. Lots of different research groups are also building their own simulators or using AI to Thor in order to train robots. So if a lot of people are already using simulation, why haven't we solved this problem already? Well, the reason we haven't solved it is the reason simulation hasn't kept its promises is that we're still operating in extremely limited amount of data when it comes to simulation. Our simulators are still very few in number in terms of the number of scenes. They have very limited object diversity. They're physically unrealistic. And another big problem that we have with work in robots in simulation is that we continue to use reinforcement learning. And if you've worked in reinforcement learning, you'll know that reinforcement learning requires a lot of manual tuning of tensor words. It doesn't scale very well for long horizon tasks, and it particularly scales poorly for large action spaces. And so if simulation hasn't kept its promises, what is the future? How do we create more and more data that we so badly need in robotics? So I'm going to give you a teaser of what we've been able to show recently. So we've been able to train a robot that we call Spock. And Spock is trained entirely in simulation, but not in the simulators that we have been using in the past, but simulators that we're able to scale now. So we have more scenes, more diversity, and a lot more trajectories. It's trained only with RGB. So this is a robot that has two cameras. The two cameras provide RGB input. We're not using any of these fancy cameras that are more expensive. We don't use LiDAR. We don't use depth. We don't build task-specific parameters into the network like mapping components. It is not trained with any reinforcement learning. There's no human data, so there's no like 17 months of data collection. It's trained with imitation learning. And what you end up getting is you end up getting a robot that can perform long horizon tasks, not just in simulation, but in the real world. Importantly, there is no adaptation to the real world. So here's a teaser video of what we've been able to do. So this is an apartment near our office that we've constructed. And here's a robot that has to go and fetch a mug. It has never lived in the real world. Everything was done in simulation. And this is an apartment it has never seen before. But as you can see, it explores, it goes, and then it goes and picks up the mug. So how did we do this? Well, the key has been scale. And this involves scaling scenes, scaling objects, finding creative ways to scale data, and finally using imitation learning. So how do we get the scale? So simulators in the past for the last decade or so have been designed manually. They've been designed by graphic designers and video game artists in order to produce, let's say, 20 different environments. These are top-down views of environments that existed in previous versions of our simulators, where you can place a robot and give it a task to perform, right? Language world, of course, has moved to like trillions of tokens, and the image world has also moved to large scale, billions of documents in image and text and video domains. And so what is the equivalent in robotics? How do we get millions and millions of different scenes that we can train simulators? And the key insight here is that we're going to generate these scenes using procedural generation. So in procedural generation, you start with an environment specification. For example, a tree structure here that says, I want a one bed, one bath apartment with a kitchen connected to the living room in this way. And then you sequentially or iteratively start generating assets that can be used in order to build a simulator within a game engine. So you can start obtaining a distribution, or you can write down a set of procedures that can give you a distribution of layouts. Then you can sample from this layout or a floor plan, and then you can produce a distribution of objects and placements and lighting and so on, and eventually build up a simulator in a game engine like Unity, where you can place a robot and then train your agents. And what procedural generation gives us, and this was called ProcTHOR, what procedural generation gives us is an incredibly large distribution of houses They're all very rich. They have lots of objects in them that can be used to train our robots. What's the downside? The downside of this technique is that all of these procedures were, so in a sense, hand designed, right? We had students in our lab who had to go in and write down procedures for how houses typically look, and then mine the web for co-occurrence relationships on what objects are typically present in these environments. And this makes it hard to scale from, let's say, house environments to conference rooms like this, right? You're going to have to go and write down procedures once again. Of course, it's 2024, and the way to scale up even further is using language models. So this is a new project that we have called HoloDeck, which uses large language models in order to do procedural generation. What this allows us to do is get much, much richer input descriptions for the desired environments. So here on the left in ProcTHOR, we used to have this little tree structure that told us what kind of apartment we have. Now we can start doing things like 3 professors' offices connected to a long hallway, and the professor in office 1 is a fan of Star Wars, right? And so doing this involves querying a large language model in the same iterative way, but using a large language model to guide your procedure generation without any human intervention. So for example, here you can start asking a large language model in order to design a floor plan, and then you can ask a language model in order to tell you what materials the floors might have, and then using off-the-shelf computer vision models in order to sort of whole fill the pieces of knowledge, do texture retrieval, do image retrieval, and start filling in your environments with assets. You can do the same thing with deciding what kinds of objects to place in what environments, and so on. An interesting thing is that large language models, as we all know, are very proficient, but are not exact. They're not perfect. And so they make lots of, let's say, physically unrealistic designs. They produce orientations of furniture that you may not actually like to sit on. You may have assets that collide with each other, their meshes collide with each other, and so on. And so we also write down a certain set of sort of global constraints and then use constraint-based optimization in order to ensure that we end up with physically realistic worlds. So here is your world of your 3 professors with a long hallway. You can see that you have 3 offices. They all have, some tables to do discussions. There's a long hallway that connects the 3 offices. And then as you see here, the professor in office 1 is a fan of Star Wars, so you have some Star Wars memorabilia in their office. And you can expand this to all kinds of environments. So I showed you offices, but you can have casinos and bakeries, and you get the idea. Large language models can really have a scale. The other thing that we can start doing is we can start using large language models to populate these environments using a large repository of 3D objects that we recently released called ObjaVerse. And so here was your completely unrealistic house. No one's house, certainly my house does not look like this. My house looks like this with my kids. And so now you can start having very rich environments for robots to live in. Right? What does this give you? This gives you a large distribution of environments in simulation. Now, how do you use simulation in order to produce training data? See, what simulation gives you that the real world cannot give you is a lot of privileged information. So the minute you build a simulator in a game engine, you, for free, get all kinds of information about what objects, what segments, what are the depth maps. You can get top-down views. You already know which objects are present in what locations, what their grasping points are, all kinds of privileged information. And so now you can write what I like to call shortest path planners, given this privileged information. Now, I just want to make it clear that privileged information is not going to be available to a robot in this environment. If you ask the robot to say, please navigate to the top of the stairs and switch off the lights, this robot is not going to know where the switch is. It's not going to know how tall the stairs are, etc. The privileged information is only used in order to obtain ground truth information in order to perform the task. But what this allows us to do is produce a lot of ground truth trajectories that can be used for imitation learning in order to produce a policy that can work without the privileged information. That is the key. So here is an example of a training data point that we have. These are the only 2 inputs. There's a front-facing camera, and then there's a side camera because that's where the arm of the robot is. This is the stretch robot with the camera on top, and this is the arm that comes out. and we can start generating lots and lots of data. So I'll very quickly go over how we created a model for this. So at every time step, you get a goal. So for example, here the goal is fetch a spray bottle and bring it to the living room. And then you have your visual observations that are encoded in order to produce what we call a goal condition visual representation. So this is at every time step. And then at every time step, this is appended with some information about previous actions and some temporal embeddings. Finally goes to a transformer decoder in order to produce your predicted actions. And this is a fully supervised approach. There's no reinforcement learning here because your ground truth trajectories give you at every time step what's the next action and what's the corresponding visual observation. And of course, doing it in this factorized way allows you to do interesting things like pre-training on web scale data to learn object appearance, and then fine-tuning the transformer decoder in order to learn the actual tasks at hand. So I want to show you a very surprising result that we have obtained. So this is an example of a training data point. A training data point is where the agent is at a particular location. And this is the task of object goal navigation. So find me something, right? So find me where my keys are. Find where my keys are. And so the planner is privileged. It already knows where the keys are. And so all it's doing is creating a shortest path trajectory in order to go find the keys, right? And so we train a model for the purpose of finding an object in an environment on 100,000 of these trajectories. All of the trajectories in our training data are shortest path. But because we're training this with imitation learning, not because. Once we train this with imitation learning, we then deploy it in unseen scenes and ask it to find objects. And the surprising thing that we see is that although it is trained on shortest path, the resulting model is able to explore rooms. So it can come here, it goes there, it explores rooms, it comes out, it backtracks, and does all kinds of surprising behaviors at inference time. And this has been a very, very interesting finding because the hypothesis was always that you could not use shortest path planners in order to produce robotics training data because that's not how your desired behavior is going to be. But turns out that even though you train on shortest path experts, you can start inducing interesting behaviors that you might need at evaluation. Then, of course, you can have behaviors that are seen in training. So, for example, here the task is to locate a computer on a sofa. And so the model goes, it looks at a sofa, it doesn't see a computer, and then it keeps exploring until it finds a sofa with a laptop on. These videos are a bit jittery because the model isn't still very good at collision avoidance. Every time it goes and collides with an object, it realizes it cannot make any progress. Then it has to sort of wiggle its way out by issuing forward, backward commands, left, right commands, get its position out of the object space, and then continue on with this trajectory. Here are some real world examples. Once again, I want to stress that there's been no real world adaptation. So it's been very nice to see that although it's trained in simulation, it's able to go and do tasks like go to a room, explore, find an apple. Then you can see there it moves its arm, takes out its gripper, it goes down and picks up the apple. And here you can see examples of finding a toilet and picking up a house plant. So I'm going to skip a little bit in interest of time. So what works and what doesn't? So it turns out that scale is key, but it's not scale. If we had taken previous simulators and just got more training data, we would not have seen this improvement. The key has been diversity. Diversity of houses, diversity of layouts, diversity of objects. But another interesting finding that we have is that the bottleneck is not planning. The bottleneck continues to be visual parsing. So here we had an experiment. So these are two different data sets where we provided the bounding box of the target object when it was visible. So for example, find my keys. I only give you visual observations, but the minute the key is visible in the frame, I tell you that that's the key that you need to find, or that's the key that you need to pick up, right? And when you provide this target bounding box in training and test time, we find that the performance goes up by 20, 30, sometimes 40%, right? What that indicates is that the skill of exploration is something that the model has already learned. See, you only provide this privileged information once you have explored around different rooms in this building, come to this room, and then see them. And it's only this last mile visual parsing that continues to be a bottleneck. And this is an interesting finding because this suggests that this method of generating training data is very useful. And it's the pre-training of visual encodings that needs to be improved in order to get this to much larger accuracy numbers. And of course, this is a graph that shows that the light green are results in simulation and the dark green are results in the real world. And we see that results in the real world. Results in the real world do as well as in simulation in many cases. Okay, and of course, here are some last few examples of the robot trained on tasks that are not just pick and place. So we're able to train robots in order to do things like opening doors and picking up some pieces of paper or at least wiping out pieces of paper from the table, which is very promising because it shows that you can do all kinds of interesting tasks using imitation learning in simulation. Okay, I have a few minutes left, so I'm going to end with a different take on building these foundation models. So
We can go closer to 12.
okay, sounds good. Thank you. Let's take a sip of water.
One question ask. You mentioned that maybe planning is not the bottleneck and it's mostly the visual processing that might be the bottleneck. Can that be the artifact of your requirements for the tasks that you define?
So in the past, when we had very limited number of simulators and limited number of objects, it was certainly the case. Because anything that was trained on simulation, when you have 20 rooms that you train on, particularly these rooms are not completely photorealistic, transfer to the real world becomes a huge challenge and it overfits to that small domain of data. Now, I don't think training in simulation is the bottleneck. I think it is simple, 101 tasks in computer vision like object identification that continue to be a problem. And so now one of our current projects is looking at, the way we are doing visual processing today is simply taking a model like CLIP or SIGLIP or one of these models that have been trained on internet scale data and applying those digital encoders onto our robots. And so now we're thinking about, is internet scale image text pairs the right way to create visual encoders for robotics? Or does the robotics domain require its own methodology of creating visual encoders? Because simply scaling up visual encoders isn't solving the problem. So I guess long answer to your question is I don't know.
May I ask one more?
Yes, of course.
So you also have experiments where given a model that was trained in a simulated environment, you upload it to a real robot for
Yes.
real world evaluation. I suppose you have to do a lot of work to make sure that you minimize the mismatch between real robot sensory information from simulated robot. I'm wondering if there's anything that you can share about the process of aligning the two.
So in this project, we've done very little work on that. The main work that needs to be done is making sure that your cameras are placed in the correct locations. Apart from that, we've not done any real work in align. Oh, the other thing that you have to do is, when you take an action like move forward, you move forward by 10 centimeters in simulation. You need to make sure that your robot moves 10 plus or minus 1. The thing that we had to do in simulation to get this working is augmentation. So you had to do a huge amount of data augmentation. You had to do, and what does data augmentation mean? It means you have to augment the pixels. You have to also augment the effect of your actions. So for example, if you say turn left by 10 degrees, you need to make sure that you have some Gaussian distribution. And sometimes you move 11, sometimes you move 9, because that's what happens in the real world. You have to do a little bit of augmentation to simulate slippage, simulate collisions, etc. But all of that is easy to do in simulation. And then it transfers to the real world. A project that we're working on now is to get away with this need of having exact information about where the cameras, because your robotics lab may use one robot and your robotics lab may use another robot. So what we're trying to do is creating universal SPOC. So if you have any set of sensors, how can you simply, in quote unquote, pip install my model and just describe in language? I have 3 cameras, one looks straight, one looks at the back, one looks down, and have a policy that is camera agnostic, sensor agnostic. So that's where we're going next. Okay, so everything that I spoke about was based on which camp you lie in, either satisfying or unsatisfying, in the sense that it was all about more parameters, more data, and more compute, right? And so this is our quest to build general purpose models, which are larger, faster, stronger. But is there an alternative? Is it possible to build extremely impressive capabilities with less data, with less compute, with less learning, and in fact, leverage models that other people have already built? So let's look at a task again that we might be interested in doing in computer vision. So consider this image and consider the task, tag all the characters in this image that are from the TV show Big Bang Theory. In order to perform this task, you would need to first detect all the faces, then look up some sort of knowledge base to understand who are the characters in this TV show, then do some sort of image text matching in order to understand which character corresponds to which image or which face. And then you'd have to do some pixel processing in order to display bounding boxes and render text onto the image plane. So what I've been talking about thus far has been performing this kind of task with a large end-to-end model, a large end-to-end model like Unified I/O. And what this model would have to learn in order to perform this task is really, it'll have to learn a few different skills from computer vision data sets, and then apply them for this task. But of course, when we are building these large end-to-end models, we're not building an end-to-end model in order to perform tagging of Big Bang Show, right? We are building models that can perform lots of different tasks. And so in order to produce all of these outputs, this model is going to have to increase its training funnel and learn a lot more skills that are required for all the tasks that users are going to want this model to do. But let's look at it differently. Instead of creating this end-to-end model, how about I ask someone in the audience or some graduate student in computer vision in order to produce this task? What this person would do is they would not train a model just to produce this task on this image. They would simply write a program, right? And so the way they would write this program is they would import some off-the-shelf detectors for faces. They would import some clip model. They would write a simple sequence of steps, a simple program, and then they would just invoke this program on the desired image in order to get the output. This suggests an alternative to building these unified systems. Instead of creating an end-to-end model that has this large training funnel where you learn skills, why not simply just write a program that, instead of learning all these skills, simply invokes these skills? So for example, if you wanted to tag these characters on this image, you would invoke a certain set of skills, and you would do this by writing a simple program like I showed you. And if you had a different skill or a different task that you want to perform, like tag the flags of Scandinavian countries, you would need some other models that you import, and you'd write a different program. This is visual programming. So visual programming is a paradigm where we use a program generator in order to generate a program based on the desired task. And then we execute this program on the task inputs, in this case, on the image that we want to tag or that we want to modify in a certain way. VisProg is our implementation of visual programming, where we use a large language model in order to produce the program. And this program is produced in Python, and it has some HTML for visualization purposes. And then it's executed on the task inputs in order to produce the outputs. And VisProg can invoke all kinds of modules and all kinds of tools that you would use in your work. So you can have neural models from Hugging Face. You can have image processing libraries that I used as a graduate student, like OpenCV. Really, any program that can be invoked is fair game for the paradigm of visual programming. And so the way it works is you have a large language model, you have a task, but then you have to provide it some information about the tools that are available for this task. So in the paper that we had last year, we provided this information through in-context examples. So the in-context examples instructed the large language model on the tools that were available and some examples on how to use these tools. And then the large language model was able to take the task that you want to perform and produce a program that would be successful at that task. An interesting outcome of this approach was that you can produce visual rationales, which means that you can take your outputs at intermediate steps in your code, and then you can start visualizing them, which of course introduces a nice property of interpretability, but also allows you to debug these programs and get humans in the loop in order to improve these programs. So this has been a very interesting way of thinking about building computer vision systems. But of course, there are two drawbacks. One is you must manually write down an exhaustive set of tools. And the second is there is no error recovery, right? So let's take a step back and think about how we actually write these programs. So although I said, well, a graduate student would simply go and write the program and everything would just work, in reality, how does this work? So if I ask one of you to write a program for a task, first of all, you're going to go and browse the internet. And you'll probably use your domain knowledge to say, well, you know, Hugging Face has a lot of interesting modules in its transformers library that are relevant for my task, maybe. Then you'll start looking at the GitHub repository. You look at documentation. You look at prototypes. You look at GitHub issues. You'll really do a little bit of a thorough analysis on this. Then you'll maybe start a Jupyter notebook. You'll start seeing how to invoke these modules. You'll make errors. You'll correct your program. Eventually, you will come up with a program that can be successfully executed on this task. This method of iterative development and code retrieval are the basis for what we're calling Visual Programming 2.0. And this is very, very fresh work that we are involved in at the moment. So I've, just a few key observations that I can provide to you at this point. Here, a large language model is an agent that interacts with an environment. At every time step, it can take an action that produces a desired output. So for example, an action can be passing it a piece of code that must be executed, in which case you get outputs of your execution. Or the action can be search, or the action can be producing a thought in language, which can be used to think of it like chain of thought reasoning in language model space. And then when it takes actions, it gets observations. So it can get an STD out, it can get an execution error, it can get a retrieval set, or it can simply get an answer, which is the final piece of code. So, So I'm going to end by just showing you an example that illustrates this. It's a little bit of a toy example in order to show you the complexity of things that it can do. So here's an image, and I'm asking this Visual Programming 2.0 model to write a piece of code that can do this fairly long set of tasks. I want you to load this image. I want you to detect all the objects in this image, but I don't want you to just run an object detector. I'm telling you that I trust this DETR model based on the ResNet 50 architecture. I want you to run this object detector. I want you to list all of the animals that are present. Then I want you to give them names based on how children talk about these animals, like cow moos and snake hisses or whatever. And then I want you to answer the question, is there an animal in this image that produces the sound woof, right? So fairly toy example, but illustrative on the long nature of this task. Here's some intermediate outputs that the model produces. So at the very beginning, it says, let me read from here. It says, the task involves multiple steps, loading an image, detecting animals, blah, 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 blah. I need to use the Facebook DETR ResNet 50 model. And so I'm going to start by searching the code base for existing code related to loading images and using the DETR model. And then it takes an action, which is an action called search, and it produces queries that are going to be used for this search. And there are certain things that we've coded up here by saying you can look for, when you say text colon, you can look for any piece of text that has this string, but you can also do code colon, you can do documentation colon in order to be able to search within code, within documentation, within prototypes, etc. And what you get from the environment is an extremely long, this is a very small snippet here, an extremely long piece of retrieval results that has code blocks and documentation blocks, etc. Once this is executed, the language model then takes the second step. And this time it executes code. It says, okay, the search results provided documentation links and some code related to loading the data model, the load image function, blah, 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 blah. And so now I'm going to produce a piece of code that can load this image and load this model. And then this is also a snippet. It produces a larger piece of code. And then it learns how to load the model and print out some tensors from this model. And so on and so forth. This example takes about 12 to 14 iterations in order to produce the code. And sometimes the model makes mistakes. So for example, an interesting mistake that it makes here is that it loaded the object detector, it ran the object detector and found no objects. And then it hypothesized by saying, well, I set my threshold for object detection very high. So maybe it asked for a threshold of 0.9 probability of an object being present. And instead it needs to lower the probability. And then once it lowers the probability, it then starts detecting more and more animals. Then it says, well, I need to load a T5 model. As you can see here, it is doing what we call iterative coding or iterative development, where it writes code, it makes errors, it corrects those errors, and finally it produces the program. And this greatly improves the accuracy on different benchmarks that we're testing and really resembles more closely the way a programmer or a practitioner of AI would start writing pieces of code in order to produce tasks. We're still at the beginning of this project, and hopefully we'll have some interesting results and benchmarks to share with you in the next few months. Okay, so in summary, we're really trying to build foundation models for vision and robotics that are as capable and that are as creative as language counterparts. But there are many, many challenges, especially as you start going into multimodal space. And so today I spoke about how do we start thinking about unifying tasks? How do we start thinking about producing the right training data for multimodal environments like robotics? And then finally, I left you with an alternative, which is saying, well, should we be building foundation models? Or should we just be leveraging foundation models that are already built in language and invoking them in creative ways in order to produce, extremely capable multimodal models? And with that, I will end. We have a long list of people who lead these projects, as well as lots of collaborators across the world who help us execute them. And thank you.
Have 10 minutes for questions.
Yes.
So in the visual program window, the feedback that you there can be errors which are not really, like standard errors or no object errors. It can be just the quality of the detection is bad, or the output, the vision model's output is not as good as it should be for the downstream task that we want to achieve. So how do you get those sorts of feedback?
Yeah, that's a great question. So execution errors, these language models, particularly the coding language models, are very good at correcting, right? So let me give you an example of something that you said. You said, so imagine I want to detect objects. Should I use a model that was produced by my lab, or should I use a model produced by your lab, right? These are not execution errors. They are sort of deficiencies of the model that I input. And so the way we are thinking of this is using large language models in order to write test cases for tasks that are similar to the tasks that I want. So for example, imagine that I want to do that cow and buffalo example, right? This means that I'm going to need an object detector that works well on images. Can I now retrieve an image for which I know grounded for animals, and at least on a small retrieval set, invoke different object detection outputs and check their performance, and then decide which object detection outputs. So once again, this is again getting closer and closer to how we think about choosing the right model in a constraint set. That's how it works.
In the visual programming world, you wrote that you can leverage foundation models and you can use those subtasks. But can these also be used in some way as a ground truth for the original unified IO kind of models, where you show that by like matching or forcibly matching embedding, you can show interpretability of the foundation models themselves?
Yeah, this is a question that we've been thinking about as well, is can we use visual programming in order to actually, you can go one step further. Large language models are already getting quite creative. So can you get a large language model to produce a set of creative tasks, use visual programming to solve those tasks, and use that data to supervise an end-to-end model? This is a really, really good question. My short answer is, I think we should do it, and we have not done it yet. I think it makes a lot of sense.
Hello.
Go for it.
Hello, can you hear me?
Yes.
Yeah, I just wanted to ask a question on the kind of a API call that you're making from all the different language models. Will it be any impact on the performance wise?
Well, if you're talking about speed, then yes. Building an end-to-end unified model that requires a single forward pass is probably going to be faster than making API calls. But to be fair, that is not something that we are focusing on at the moment. We're focused on improving the accuracy of your downstream system.
Yeah, thank you.
One last question before we break it.
Yes.
But my just problem of the scale of my two solutions might be, but instead of training heterogeneity robot, why not just train human robot? So that we can have a family of like internet scale data video about human proposal of task. And now the problem is not the data set, and the problem is actually matching from human videos, the human movements to the human or robot action. So that I think this is an easier task. So instead of creating a simulation of
Yes.
is there any technical challenges?
Yes, that's a really, really good question. So there is the technical challenge there is understanding the action. So you can get observations. So particularly with a lot of egocentric data sets, right? There are data sets collected by, for example, Facebook, where there are cameras on top of human beings doing tons and tons of actions. And so you can get data for where the arm moves, and then what observation you get at the next step, right? So here it is a bit easier to understand the location of your arm, and then you can use something called inverse kinematics in order to say, well, I think this was the action taken in order to produce this modification in the arm position. But when you go to internet scale data with third-party view, it is still human pose estimation isn't as accurate as it needs to be in order to produce the actions that that human being might have taken in that video. But this is definitely the future, is transferring knowledge from internet scale human videos in order to produce supervision for robotics. The other challenge is that although humanoid robots sound great, humanoid robots are actually harder to train because there's a huge issue of balance. There's a huge issue of like, you have to like leave one foot and balance on one foot as you take your next step. So actually it is easier to create from a physical point of view, robots that are non-humanoid, but it's easier to get training data for humanoid robots. And so there's also work in the robotics community on how to transfer action spaces from one embodiment to the other. That way you can leverage human visual data, but create robots that are easier to operate, easier to build, easier to repair, and so on. But yes, your intuition is absolutely right.
Let's thank Ani one more time.
Thank you.
Great presentation.
Thank you. Should I leave?
Yes, we can leave here and we are. Just gonna, so one of my colleagues wanted to end here, so
Sure.
what I did was I'm gonna swap my slot with them. But we don't have time over dinner, so I'm just gonna cross it up here so that I keep.
Sounds good.
Thank you for the talk. I'm one of the students who's taking you to lunch in a couple of minutes.
Okay.
One of the students unfortunately had to cancel last minute, but
Okay.
when she was something else.